Hey everyone, so we will go ahead and jump right into section 1 of Unit 1 today. Hi everyone, this is section 1 of Unit 1's notes. So this is a review of basic function ideas, and if you watched the intro video, you'll remember that I mentioned this is really focusing on domain of functions, and within that topic is how to write domains using interval notation. So we will get to that here in a minute. First, we have a review of the definition of a function. So the definition of a function is that it's a correspondence or a mapping between two sets of things. So set A and set B, where one element in set A corresponds to exactly one element of set B. So it has to be exactly one and not more than one element of set B. If you remember the vertical line test, and you have a function that looks like this, the vertical line test would be checking to see if that vertical line passes over that graph more than one time, it's not a function. And if it did, that would mean that one of the elements from the input, say we looked at something like this, that would mean that one of the inputs, meaning this x value, mapped to two different y values. So they can only map, input values can only map to exactly one output value. So another visual here that I like to look at is, say I have a set of my x's or my domain values. Remember, domain is input of a function. And each of these values is mapped to exactly one value in the range or the output. So this value right here maps to one value over here, this one maps to one over here, and however many are in the domain will map to exactly one. And what's happening to these values from the domain, we're not sure, but there's some function that's changing them to the output value. So there's a little visual of, a couple visuals of what a function is. So like I already mentioned, domain of a function, those are our input values. Typically we use x's for that. And this is the independent variable. X's in domain is independent of the range. Independent. Then we have the range, which would be the output values. My handwriting is really bad on here still because I'm still trying to get the hang of this. And our output values, typically we use the letter y for those, and those depend on whatever the input is. So y would be the dependent variable. So just a quick review on that stuff. Now we've got two different types of functions to define. One type of function, you guys have seen this first one, a function whose domain is and range is a set of real numbers. So real numbers are continuous and infinite. Even between the numbers 0 and 1, there are infinitely many real numbers. So it's continuous and linked together. So these are considered real functions, which is what you guys have been looking at. And they're smooth, continuous functions with a smooth graph. A function whose domain is any subset of integers, not real numbers, that would be considered a discrete function. So these are not continuous functions, if you want to think of it that way. It's choppy. The graphs are choppy and they're not smooth and connected. Real functions are what you guys have been mostly looking at up until now in math. So examples of real functions, which are those smooth, connected, continuous graphs, would be linear functions, so lines. So linear. Also the quadratic functions that you graphed a lot last year, or the year before, whenever you did quadratics. Another type of real function would be polynomial functions, so higher ordered polynomial. Trig functions. I know you're all super happy to hear the word trig. So your sine waves, cosine waves are continuous and real. Also, exponential functions, logarithmic functions. So these are a lot of what you guys have been looking at over the last couple of years, and those are all examples of real functions. Discrete functions are, like I said, not continuous functions. So I like to just think of them as choppy functions. They're not smooth. Examples of discrete functions would be sequences. And a more real-world example would be a function that you might be comparing year to population. So the years are not continuous. It's 1 year at a time. So those are those integer domains. So year versus population. And anything else where that domain is not a smooth, continuous set of input values. Next, we're going to look at how to represent different intervals or sets of numbers using different types of notation. So here in this left-hand column, you see set notation. That's where you define the variable x such that x is greater than or equal to 1 and less than or equal to 8. So that's one way of representing an interval of numbers using set notation. To represent that same group of numbers using interval notation is where you have to decide, am I going to use brackets or parentheses? And that depends on whether or not those outside numbers are included in your set. So in this case, since x is greater than or equal to 1, we have our lowest value of 1, our greatest value of 8, and since 1 is included, we will use brackets on that. 8 is also included, so we'll use brackets on that. So this should be a review for all of you on how to write these. And then the graph column over here on the far right is just what does this look like visually on a number line. So we're talking about all the numbers between 1 and 8. So we are including 1, so we would have a closed circle on 1, closed circle on 8, and it's everything in between there. So 3 different ways of representing these groups of numbers: set notation, interval notation, and graphing. Interval notation is what we're going to use pretty much all year when we're talking about intervals. So the next example is x such that x is greater than 2 and less than or equal to 9. So again, we start by writing our, I just discovered how to use different colors. So we start by writing our lower boundary, comma, upper boundary. Our lower boundary is not included. X is strictly greater than 2. So we use a parenthesis there, and that signifies that we are not including the value 2. It's just everything greater than 2. 9 is included, so we use the bracket there. So again, this interval notation is representing that same group of numbers from the set notation. On a number line, that would be everything from 2 to 9. We're not including 2. So that would be an open circle, closed circle on 9, and everything in between. The next one is z such that z is greater than or equal to 3. So if z is always greater than 3, that would mean our lower boundary is 3. Since z can be anything above 3, that means we're not bounded on that right side. So it's going to go all the way to infinity. So you can see that 3 is included because it can be greater than or equal to 3. So we're using the bracket to include it. You can't technically include infinity because it continues infinitely. So that's always a parenthesis with infinity. To graph this on a number line, you would just make the note of 3 being included and then shade everything to the right all the way up to the arrow, which indicates it continues. And then w is less than 4. So if w is always less than 4, that means 4 is the absolute highest that set of values can be, but we're not including it because it says that W is strictly less than. If 4 is the highest and it can be anything below 4, that means we can go to negative infinity, and we cannot include that, so that's a parenthesis, not bracket. On a number line, we've got 4. We cannot include 4, so that would be an open circle and shade everything left. So really the most important column here is this review on interval notation, which is how I'm going to expect you guys, unless noted otherwise, to write domain, range, and any other intervals that we're talking about. When asked to find the domain of a function, you really have to be thinking about that specific function and why we might need to limit the domain. Sometimes certain input values just won't work for certain functions, and that's when your domain is not going to be all real numbers. You're going to have to analyze what values would not work for it. So these are the main reasons to think about why your domain would be limited. So the first example is just certain values don't make sense. So just thinking about it logically, if it doesn't make sense, you can't use it in the domain. An example of that would be, say your input value was time. Say you were comparing time to distance. Time can't be negative. So you'd have to limit your domain, say your domain was t, to be greater than or equal to 0, because you're not going to go backwards in time. Another one would be distance. If distance is your input, distance cannot be negative. So distance would have to be greater than or equal to 0. So that in that case, it just wouldn't make sense, and you'd have to limit your domain. Another example would be square roots. So this is one of the bigger ones to keep your eye out for. You cannot take the square root of a negative number. So anytime you do have a square root function, say I have the function f of x equals square root of x minus 3. There are certain values that when I plug them in for x, I will get a negative in the square root function, and those values won't work for our domain. So we will, on the next page, review how to limit that domain. Another big one that you need to keep your eye out for would be when you have division in a function. So any rational functions, meaning you've got a division bar. So for example, if I have a function that looks like this, x squared divided by 2x minus 1, you can't divide by 0. It's an undefined function. So this cannot be 0. So we'd have to solve for when x made that 0 and limit the domain in that way. And then the last one is if the definition of a function is restricted to begin with. For example, and it's okay if you don't remember this, we'll have plenty of time to practice it. The log function, say I had a function f of x equals log base b of x. That function is only defined for positive values of x. You can't take the value of a negative number. It doesn't exist. Or the log of a negative number. So this is only defined for positive values of x by the definition of a logarithmic function. So these two things are what you really need to keep your eye out for, especially in this section, when you have a square root in a function or when you have a division bar. You cannot divide by 0. All right, if we turn the page, examples, and each of these examples we're just asked to find the domain of the function. So just like I talked about a second ago, we're looking for possible reasons that domain would be limited, figure out the limitations, and represent the domain using interval notation, so the notation that we just talked about. The first one is fairly simple. This is a quadratic function you see from the leading term x squared. And if you remember, a quadratic function is some form of a parabola. So parabolas are real functions, and this already says all of these are real functions. So if you look at the graph and think about values, do I have any limitations on squaring a real number? I can square any real number. I can multiply any real number by 3, and I can subtract 7 from any real number. So this function does not present any reason we should need to limit the input. So in this case, we can use all real numbers for input here, which would mean my lower bound would be negative infinity, and my upper bound would be positive infinity. So that's the domain for that function. Another way to represent positive or negative to positive infinity is by writing the symbol for the set of real numbers, which is an R with that double line or a bold R. So that one's fairly simple. The next one is, I'm going to go over to the right, g of x equals the square root of x. So radical signs are a red flag when it comes to thinking about domain. Remember, we can't take the square root of a negative number. So whatever is on the inside of that square root, in this case just x, cannot be negative. In other words, x has to be either 0 or greater than 0. So this is basically my domain. I just need to represent that using interval notation. So x can be anything as long as it's greater than or equal to 0. That means the lower bound is 0, my upper bound is infinity. I can include 0 in this one, I cannot include infinity, so that's the domain of that function. If you look down to h of x, this is similar to the g of x problem I just did, but it's got an extra term here underneath the square root. So right now our function is the square root of 5 plus x. Remember that we can't take the square root of anything negative, so that whole thing, 5 plus x, would have to be greater than or equal to 0. So write that exact statement down. 5 plus x would have to be greater than or equal to 0. And then we're just solving for x. So we'd subtract 5 from both sides, and we can conclude that x has to be greater than or equal to negative 5 in order to guarantee that we wouldn't take the square root of a negative number. So if x has to be greater than or equal to negative 5, that means my lower boundary is negative 5, and it can be anything greater than that. And I can include negative 5, so that would be the domain for that one. On to j of x, another square root function. So this time what's inside of our square root is 9 minus x squared. And that whole expression, 9 minus x squared, would have to be greater than or equal to 0. So again, to find our boundary or limitations on x, we need to solve this inequality. And when you're solving inequalities with exponents greater than 1, it gets a little tricky at times, so I'm just going to break it down one step at a time. So first, I want to get x squared by itself, and to keep my x's positive, I'm going to add x to both sides. So that would mean 9 has to be greater than or equal to x squared. I think it's easier to think about inequalities when your variable is first. So I'm just going to reorder this. So technically x squared has to be less than or equal to 9. So that's really what we're looking at. Now if you think of something, a number x, and I square it, and it has to be less than or equal to 9. Well, we all know that 3 squared equals 9. So if I square anything over 3, the product will be greater than 9. So it definitely cannot be larger than 3. So x needs to be less than or equal to 3. But remember, when you're squaring numbers, you can square a negative number and it will become positive. So if you think about it on a number line, if I square anything between positive 3 and negative 3, I'm going to get a positive number. So technically I could go all the way down to negative 3 and square that too, and it would still be less than 9. So that means I can square any of these numbers and they'll be in between, or they'll be less, the product will be less than 9. So our limitations on x are that it needs to be in between negative 3 and 3, and that can include those values. So negative 3 to 3. At this point, you've seen, well, let me do one more, and then I'm going to have you, hopefully you'll stop this and try and do some of these on your own just to see how you're doing. So we'll do one where the denominator can't equal 0. So k of x down here, this is a rational function, so we've got a division bar in there. So 1 divided by x plus 4. We don't have any limitations on x other than that this, you can't divide by 0. So that's another one of these I'm going to put up here. You cannot divide by 0. So division by 0. These are the two main things you're keeping your eye out for. X plus 4 can't be 0. So write that out in math symbols. X plus 4 can't be 0. So that means if I think of just solving this, I would subtract 4 from both sides, and x can't equal negative 4. That's the only value that when I plug in, I'll get 0 in the denominator. So my domain in this case, and I'm going to run out of space here, but I can use any values except for negative 4. That means my lower boundary would be negative infinity, and then I get to 4 and I can't include it. Negative 4, and I can't include it. So I'm going to use parentheses at negative infinity. I cannot include negative 4, so I'm using parentheses. But I can also use everything above negative 4. So that's where the union symbol comes in, because I'm going to combine these two intervals together for my domain. So then I have another interval for my domain, and that would be everything from negative 4 to infinity, but I can't include negative 4. So it seems like a lot of extra work, but to represent the statement x cannot be negative 4 using interval notation, you need to write out the intervals of x that will work, and you're excluding 4 by making, or negative 4, those boundaries. So at this point, now you've seen a lot of examples that basically cover our two main things. We're looking out for radicals and division by 0, and we're looking for limitations on the domain. So I will continue working through these, but I would encourage you to pause and try these last 4 on your own and see how you do, and I'll talk through each one. Alright, so m of x equals 1 divided by the square root of x plus 3. Let me draw this. So now we've got a couple different things happening together. We've got something where we have a fraction, so that would mean this whole denominator, the square root of x plus 3, cannot equal 0 because you can't divide by 0, but we also have a square root. So whatever's on the inside of the square root, which is x plus 3, has to be greater than or equal to 0. So both of these things have to be happening. Both of these restrictions apply. So if you think of when this first one, the square root of x plus 3 can't be 0. The only time the square root of x plus 3 equals 0 is when you're taking the square root of 0, which would mean x has to be negative 3. So this right here means x can't be negative 3. That would mean I would be taking the square root of 0, which is 0. For this one, you just solve it by subtracting 3 from both sides, and your limitation would be that x would have to be greater than or equal to negative 3. So you have these two limitations. Whoops, this is negative. X can't be negative 3, and x has to be greater than or equal to negative 3, and you need to combine these together. So this is saying that x has to be greater than or equal to negative 3, but this is specifying that you can't actually use negative 3, which means x has to be greater than negative 3 and not include it. So that means our domain is everything from negative 3 to infinity, not including negative 3. All right, moving down to n of x. We have 5 divided by the square root of 9 minus x squared. So again, we've got a division bar, so we need to avoid division by 0, and a square root, so we can't take the square root of a negative. So we've got those two things happening, but you'll see you can combine those into one step pretty early on. So we've got that the square root of 9 minus x squared can't be 0. The only time that will happen is if 9 minus x squared itself equals 0. But because 9 minus x squared is on the inside of a square root function, 9 minus x squared has to be greater than or equal to 0. But because we already know from here it cannot equal 0, that just leaves us with the restriction of 9 minus x squared has to be strictly greater than 0. And then we solve for x in this situation, which if you look back up to the example of j of x, now we're in the same spot we were there. So if I solve for x here, I end up getting 9 has to be greater than x squared. I like to rearrange that. So x squared has to be less than 9. That means when I square a number, its square has to be less than 9, and 3 is the number that when we square we get 9, but we also get 9 when we square negative 3. So in order for the square to be less than 9, it's going to have to be in between negative 3 and 3, and we aren't including those because x is strictly less than. Alright, now we have p of x. So in this case, we're looking at another rational function where our denominator can't be 0. So we don't have a square root in this, which is kind of refreshing. So our only limitation is that our whole denominator, x squared plus 2x minus 3, cannot equal 0. So we need to know for what values of x will that equal 0. So basically we are going to solve this quadratic. So if you think back, how are we going to solve a quadratic like this? We would first see if we could factor it, and we will. So, but we don't want it to equal 0, so we are essentially just solving for when it equals 0, and then our limitations will be for those two values. So how are we going to factor this? What multiplies to negative 3 and adds to 2? So we definitely know these two first terms are x. My two last terms need to multiply to 3. My only options are 1 and 3. And then we figure out signs based on these signs here. So x squared plus 3x minus 1x would get us that function. So now I solve for x, and this means x cannot be positive 1 and x cannot be negative 3. So now the fun part would be taking these restrictions and writing them out using interval notation, because we want to represent this domain using intervals. So if you think about all the values we can use on a number line, we can use any value infinitely small all the way up to negative 3. So that would mean our first interval would be negative infinity all the way up to negative 3. And then we can't use negative 3. We pick up at negative 3, and we can use any number above that other than 1, so that creates our next interval. And then after 1, we can go infinitely large. So these are the 3 intervals. So 2 restrictions here. These 2 restrictions create 3 intervals for our domain. Alright, and finally our last one here, we are combining the restrictions of division by 0 and a square root. So remember, this whole denominator, the square root of 4x plus 3, cannot equal 0, but also the inside of that square root, 4x plus 3, can't be negative, so it has to be greater than or equal to 0. But since this is telling us that it can't equal 0, it's going to be strictly greater than 0. So we are solving for x in this equation. 4x plus 3 is strictly greater than 0. Subtract 3 from both sides. 4x is greater than negative 3. Divide by 4 and you get the restriction that x has to be greater than negative 3/4. It can be anything greater than negative 3/4. So interval notation is negative 3/4 to infinity. So that's that, and your homework will be similar to what these notes look like. Your homework is not this, because this is bookwork and you guys don't have books yet, although I did post a link to the book on Schoology, but I'm going to go ahead and just make a worksheet and post that here pretty soon. So that's 1, 1, and keep an eye out for 1, 2, and I'll get that posted soon.